Hey guys, in this lesson we're going to be studying the relationship between pressure and volume, and we'll need to analyze how pressure affects volume, how volume affects pressure, because they both have a relationship. And if we have time tomorrow, I'll also do a demonstration for you. So there's no homework associated with this lesson, but you do need to copy down this aim as the first item on your classwork page of your notes. So you should have your Cornell notes for one page and another page with just classwork, and then the aim goes at the top. And right below that include these do now questions. Don't answer them. Okay, pressure versus volume. The animation doesn't play in the video, so I can show you in class tomorrow, but the question reads, what happens to the volume of the container as pressure is added? So basically what happens is that you'll see weights being added to the top of the container. So the notes I added were just some things that I think are logical and true in black, and then in red, the heart of the matter. So I said that weights were added to increase pressure. That's what we're going to be adding weights to the top of this. And then that added pressure causes more collisions. So it's more collisions are increasing as the volume decreases. Oops, I messed that up. So I changed that to decreases. But remember, the heart of the matter is as pressure increases, volume decreases. So we're going to draw the plot line in the chart to the left. The plot line would look like this. And it would be a nice, smooth curve. This is the best I can do, guys. What it doesn't do is it never reaches a volume of 0. And the reason for that is that particles of gases actually do have some size. They take up some space, so you can't compress them down to 0. And the shape of this graph is also something that you have probably seen in math. It's called an inverse proportion. I'll show you an example. In the equation y equals 12 over x, we have an inverse proportionality because y is in the numerator and x is on the other side of the equal sign and in the denominator. That's what's meant by inverse proportion. And I can show you some values right now. If I give you certain values of x, we can get certain values for y. So I put in some values that x could be, 12, 6, 4, 3, 2, 1. And we're going to fill in values that y would be in that case. So if x were 12, y would be 1. If x were 6, y would be 2. If x were 4, y would be 3. If x were 3, y would be 4. And if x were 2, y would be 6. Now I'm going to quickly graph this. Oh, and if x were 1, y would be 12. So I'm going to quickly graph this. And I will zoom in to make it a bit easier. So here's my graph and also my values. So again, if x were 12 and y were 1, then we would be talking about this data point. If x were 6 and y were 2, we'd be talking about this data point. If x were 4 and y were 3, we'd have that data point. If x were 3 and y were 4, we'd have this data point. If x were 2 and y were 6, we'd have that data point. And if x were 1 and y were 12, we would have that data point. And when you connect these with a smooth curve, you can see that we have the exact same shape that we previously drew on this slide. So you can compare the two here and here. So it's more than just that gas molecules take up space and can't be compressed to 0. It's also fundamentally this is an inverse relationship between pressure and volume, meaning when one goes up, the other goes down. And that's the same thing with x and y. When one of them goes up, the other goes down. So like if x goes up, y would go down. But in the data I showed, x was going down from 12 to 1, and y was going up from 1 to 12. So that's the fundamental nature of an inverse relationship, and they will always take this curved shape. The Regents do expect you to know that, by the way. All right, so straighten this out and finish the slide. So the relationship between pressure and volume is inversely proportional. It is inverse because as pressure increases, volume decreases. And some people will call this an indirect proportionality, but I doubt you'll see it on the Regents. Example or not? Let's play this game again. After a bullet is shot at an innocent bunny, the bullet travels at unchanging velocity until it reaches the bunny. I'm going to go with not an example, because in order for this to be an inverse relationship, one thing goes up and the other thing would have to go down, and I see that the bullet is shot at constant speed. All right, so example or not. After the bullet reaches the bunny, it travels slower and slower through the bunny's body as time increases. So as time goes up, the velocity goes down. That's an inverse relationship. So this is an example. Good. All right, volume versus pressure. This is an animation as well that I'll have to show you in class, but basically if the container is the volume shown, so if you see this volume, and the particles are going back and forth like this at constant speed, then the number of collisions they're going to have with the walls of the container is going to be some certain rate, and that's going to determine the pressure as well. So they're going like this. But if I were to increase the volume of the container to a new volume, such as the one shown, and let the particles keep moving at the same speed, but inside a larger space, you will see that the collisions decrease. I'll try to show that to you now. So moving at about the same speed, the cadence of the collisions is lower, or there are fewer collisions per second. And that's entirely because the volume went up. So since the volume went up, the collisions went down, and so the pressure went down. So now we know that you can change the volume, and that will also change the pressure. And it's still an inverse relationship. So increasing the volume is going to decrease the pressure. And you probably know that decreasing the volume would increase the pressure because it would cause more collisions. So if I increase the volume of the container, which is what we just did, the particles on the inside would collide with the walls less often. Therefore, they would exert less pressure. So I'm saying right now an increase in volume is a decrease in pressure. If I decrease the volume of the container, the particles on the inside would collide with the walls more often. Therefore, they would exert more pressure. So now I'm saying if I decrease the volume, I'm going to increase the pressure. So both this one, an increase in volume, is a decrease in pressure, and this one, a decrease in, oops, I forgot my V. A decrease in volume is an increase in pressure. Both of those are true. They're both inverse relationships, and they both are something you should remember. Okay, so we have a demonstration slash class activity for this day. We'll need to use these Boyle's Law apparatuses. I have some tips that I want you to write down before we start the thing. So the Boyle's Law apparatus we're using today has a loading platform, which is either one of these blocks. And on the top, we'll use weights like books, for example. So our weights will probably be textbooks. And we also have a volume-marked chamber. So that's how we'll measure the changes in volume as the pressure is changed on top of the loading platform. So when we add weight to the loading platform, we're increasing the amount of pressure. So what we'll probably notice is a decrease in the volume. So on the end of this syringe cap, or down here, well, there'll be a syringe cap, a little thing you can twist on and off to push air out. So you'll twist it off, and you'll set the volume to 30. It's difficult to know where to set the volume, but you can see that there's a rib on the plunger here, and there's a second rib behind it. This rib that I'm marking in red, that's the one that you're going to set to 30 milliliters. So have that written down and prepared before class that you're going to set the leading rib to 30. And then you're going to assemble the apparatus by basically, after it's set to 30, sliding this block onto the end of the syringe plunger, and then twisting the front end of the syringe into this block. And then you're going to get some partners. You're going to add books one at a time to the loading platform. And after you add each book, you'll just quickly tap it just to make sure it's not stuck. And then you're going to measure and record the volume of the gas in the tube after each of the load and taps. You're going to need to record this data table. And it basically just says how many books you have on it. So you'll start with 0. The volume should be 30 if you set it correctly. And then the volume will change as you add more books. And we'll do that in class. And then you also need to prepare a very nice graph with equal spacing. And the pressure is going to be measured in books. So we have 0 books here, 1, 2, 3, 4, up to 5 books. So pressure is in books. And the volume is going to be measured in milliliters. And then copy down this question as well. I also want you to copy down this particular pair-up. It's just a continuation of the previous pair-up. And there is some hidden text here. This one right here, it says, as pressure increases, volume blank. And then you can see this one, as volume increases, pressure blank. So get all of this stuff copied down. And then lastly, copy down the summary questions. And then you'll be ready for class tomorrow. Thank you for watching. Have a great evening.